Continuing on the theme of networks and development, we have Emily Breza, my colleague in the economics department. She is totally amazing, works on extraordinarily difficult questions at the intersections of financial and labor markets and social networks and development. She's cross-appointed at the Jameel Poverty Action Lab, the National Bureau of Economic Research, the Center for Economic Policy Research, and the International Growth Center. Did I miss any? Before joining Harvard, she was at Columbia Business School, and prior to that, she completed her PhD at MIT in 2012 and her bachelor's at Yale in 2005. She is also very distinguished. Among her accolades are the Brattle Group Prize for the best paper last year in the Journal of Finance, and the fact that she has received a new NSF grant every year since completing her PhD. Which is like totally extraordinary, and for the mathematicians in the room, economics professors usually write a total of like 0 NSF grants. So this is like, they're very, very hard to get in economics. So this is sort of, upweight even more by some sort of like logarithmic to exponential inversion. But also particularly appropriate for this audience, she received the DeForest Prize in math. So she's going to be telling us about feasibly identifying network structure without network data. Let's welcome Emily.
Thank you. That intro was way too kind, and thanks so much for having me here. So this is going to be an empirical paper, and I will do a lot of motivation, the opposite of Mohammed's strategy. Our goal here, and this is, I should say, with some statisticians and another economist, Arun Chandrasekhar at Stanford, and then the statisticians Tyler McCormick and Mungji Pan at the University of Washington. Okay. So we're going to come at this from a point of view where we think that network data is really useful for lots of reasons. So one of them is this diffusion idea, identifying the right individuals. Now, after reading Mohammed's paper, I think we might want to update that to thinking about what the right model of diffusion is. And are we in a threshold model type world, or are we in a world where just random might as well outperform or perform almost as well as targeted seeding? We might want to think about understanding whether there are systematic failures in social learning. Strategic incentives to communicate, for example, might be one. Studying patterns of risk sharing or informal lending, assessing financial contagion, decomposing job referrals, or measuring peer effects. So all of these things are questions where having network data can be very, very useful. Now, the problem is that collecting the network data itself can be very expensive and unrealistic. And I gave a talk to some PhD students a few summers ago at a summer school, and I was going through the literature on network field experiments, and one of the pieces of feedback they gave me was, okay, this was really interesting, but how could I ever run any of these experiments myself? This isn't a literature for me. You need to have a lot of money. You need to be well established. I'm not going to be in a position to collect this kind of data, so while this was fun, I'm going to just sort of discard all of this research. So one of our goals here is to try to do better and open up the ability for other groups to do this work. And so, for example, the network data that Mohammed was using as his motivating example, where they have data from 75 villages and 16,000 households that cost about $250,000 per wave. And so that's quite expensive, prohibitively expensive for a lot of economist budgets. Also, there's been a real proliferation of research around data sets that exist in the public domain. So for example, AdHealth, this is a data set of adolescents in classrooms. This is one where network data exists, and there have been hundreds of papers using that data. Now, of course, adolescents in high schools in the US are interesting, but I think that being able to expand the types of populations we study is also a nice goal. This problem also leads to policymakers using demographic proxies, which sometimes work and sometimes don't really work at all when trying to design policies. And there's been a little bit of work showing that indirect survey methods can be a lot cheaper. So one thing you can do if you want to estimate who's central is you can just go ask people. So this is what Banerjee et al. 2016 do. They say, well, if I wanted to go spread information about a job, who should I go talk to? Who would get that word out the fastest? And it turns out that that's pretty good at shortcut instead of needing to collect the full networks. That's great for something that looks like centrality. And then aggregated relational data is what we're going to think about. This has been shown to be really useful for measuring degree, among other things, but we're going to actually take that idea, that insight of collecting aggregated relational data, and I'll explain what that is in just a second, and really using it in a lot more, to do a lot more than just estimating degree. Okay, so what is aggregated relational data? So our goal is going to be to use aggregated relational data as a sufficient statistic for thinking about measuring the broader network. Okay, so I'm a development economist, and so the typical application of interest for me would be a village, and I work a lot in India. So here's an example from India. So think of all of your friends in this village, and it's important to really, philosophically define what you mean by a link, and so we would telegraph that to them as well. Okay, so of this list of people you've just thought of, how many of them own a tractor? And you can ask this for lots of different types of traits. How many of them have two-story house? How many of them have electricity? How many of them have children who finished high school, for example? Okay, so what we're going to do is we're going to extend the ARD approach that my co-author Tyler and other statisticians have worked on to think about general network formation model. So that'll allow us to actually estimate any arbitrary node level or graph level network feature. And then what we can do, once we've set that up, and I'll show you what our model looks like, we can ask how well this aggregated relational data method does when we know the actual network, right? So how well are we actually able to recover things? And so we can show a proof of concept with real world data, and then the thing that makes me even more excited is we can replicate some experimental results from some work that we've done elsewhere. And so our goal here is to create a blueprint for relatively inexpensive, useful network elicitation without needing to do this $250,000 mapping exercise. And so while it's not free, we can show, if we get people in the field to put together budgets for us, that our method's about 80% cheaper. So hopefully this is something that other people can use. And we put all the codes up on our websites, and they're available for free use. Okay. So I'm going to summarize the idea, and then I'm going to walk through our model. So the first thing that we're going to do is we're going to think about a specific network formation model that we have in mind. And in that network formation model, nodes in the network are situated on some latent space. And so think about the surface of a sphere. That's what we're actually going to use in our estimation. So the probability of any two households in this village in India situation having a link is going to be decreasing in their distance on this latent space. So then we're going to give a sample of nodes in this network a bunch of ARD questions. So let's say 7 or 8 of these ARD questions. How many people do you know who own a tractor type questions. That's going to allow us to map where the trait groups live on this surface of the sphere, and also where each individual lives on the surface of the sphere. And so we're going to use these ARD questions to fit this map, this latent space map. For the people who aren't asked the ARD survey, we're going to be able to, use some methods to try to, to put them also on the surface of the sphere, just asking in terms of demographics, who are they most similar to? And people like them, where do they live on the surface of the sphere? So once we have all of the people plotted on the surface of the sphere, and our network formation model is just saying my probability of linking is going to be a function of our locations, then we can get the distribution of underlying graphs. So then we can identify who might be central. We can ask, does the graph have a big cut in the middle? Would information flow well in this type of community? Is this network likely to be very segregated, et cetera? Any sort of arbitrary question. Okay. So this is an example of a map. So this is the surface of a sphere plotted on 2 dimensions. And this is from some actual data that we collected in Hyderabad, which is a large city in South India. And for this, we thought of a neighborhood as a unit of analysis. So this is from one specific neighborhood. And we asked questions, how many people do you know who've ever been arrested? How many people do you know who've ever remarried? How many people do you know who've ever given birth to twins? How many households do you know that are engaged in polygamy, et cetera, et cetera? And so then what we can do is we can triangulate from those questions where each of these trait groups lives on the surface of the sphere. And how dispersed that trait group is, right? Is this something where they're really spread out all across, or is this something where everybody is very close to the center of their groups? And just staring at this, actually, this type of arrangement makes some sense. So it turns out that remarriage and arrest are both a little bit countercultural, and so those two groups seem to be quite correlated. government employees and people who've sent a child abroad are actually quite correlated in terms of where they're living, and that makes sense to us because those are both things that are associated, at least in slums, with higher levels of wealth. And twins and polygamy are also seem to be closer together, which might make sense if there are more women in a household. There's just a greater likelihood that that household has a set of twins attached. So what happens is we get a different map for every single neighborhood that we survey, and this is the basis for our model and for trying to actually estimate the full network. Okay, so what do we have in mind? So typically, like the Banerjee et al. Group, when they go collect network data, they'll look at the entire n nodes, all n households in the village. They'll ask everybody a series of questions, and they'll do a really complicated matching in the field where they are able to connect all of these links and really measure this. And the matching part is actually what makes it so expensive. What we have in mind is actually taking just a subset of these households, asking ARD questions, and where we don't observe the graph at all. And what we want to do is we want to show that ARD questions are sufficient to actually reconstitute a lot of this network structure. Okay. So I'm going to go through the method quite quickly. The details are in the paper and also in the earlier work by my co-author, Tyler. But I'm going to just try to do this at a high level and then show you how well it performs for the types of applications that I've worked on so far. Okay, so the first thing that one would do if you're going to go try to implement our method is to collect ARD questions, an ARD survey. So ideally, you'd go to some share of nodes, let's say psi in a network, and ask them this list of, let's say, 7 questions. How many people do you know who own a tractor? So we're going to sample a share psi. Think of this as like 20 to 30%. If you do less than 20%, it turns out that you don't have enough information to really constitute, to be very certain about where these different groups live and where the different individuals live in the network. Now, an ARD response is just going to be a count, right? To how many people do you know, how many households does your household know with trait K? And so we can think of that as just summing up over all of the individuals, so for individual I, this is summing up over all the individuals J who have actually that trait K, and asking, is there a link? Okay, so the example, my motivating examples are going to typically look like village social networks and attribute classes, but you could think about using this in other places like firm supply chain networks and banking networks, and we're thinking about undirected graphs here. Okay, the second step, if we're actually going to go do this, is we're going to need to map some information about the entire population. Now, ideally, you would do a census exercise for all nodes, and you would calculate at least, does this person actually own a tractor, and then maybe some other demographic characteristics. But I'll show you actually, this isn't absolutely necessary for times when this is infeasible. But it's really nice to be able to have this. Okay, so then the third step is to say, okay, now we've collected all this survey data. How do we take the ARD questions and estimate a network formation model and then eventually draw the graphs? So what we want to do is we're going to first write down the network formation model that I talked about loosely. So the probability of a link forming between any 2 nodes is going to be a function of the news, which are gregariousness parameters. So how gregarious household I is, how gregarious household J is. That's going to be typical in a lot of network formation models. And then the third term is going to be the closeness of these households in the latent space. So the Z's, Zi and Zj, are going to be the locations of the households on the surface of the sphere. And zeta is going to calibrate how much the likelihood of a link decays with distance. Okay. So the key assumption, as with a lot of network formation models, is conditional independence. So given these latent positions, the link probability is independent. And so that's going to be really helpful, and that's going to be something that is true of most any network formation model that's tractable that you would want to write down and use in a setting like this. Okay, so we're going to do this in a Bayesian framework because our co-author Tyler is a Bayesian statistician. So we need to say something about these trait groups and how what are our priors for how individuals are scattered on the surface of the sphere. So we're going to use von Mises-Fisher distributions. Now, what are these? You can think about these as like little bell curves on the surface of the sphere. So they're going to have a center, they're going to be symmetric, and they're going to have a concentration parameter. So we're going to assume for our prior that the individual locations are going to be uniformly distributed on the sphere, right? So they're just going to be equally likely to be found anywhere. And then the trait groups are going to be distributed with a center, nu k, and then a concentration parameter eta k. So these parameters are going to be important ones that we need to estimate in our estimation strategy. Okay. So now, once I've told you what our network formation model is and how we're parameterizing how the groups are tiling on the surface of the sphere, we can think about putting all the pieces together. Okay. Now remember, what is ARD? ARD is just a count, is the sum of the indicator 0 or 1 for whether there's a link with any given person of that trait group. And conditional on these latent positions and gregariousness, since these are just counts, these YIKs, the ARD responses, are going to approximately follow Poisson distribution. Okay. So equipped with this, McCormick and Zhang, so Tyler and his co-author in their 2015 paper, show that the expected ARD response can just be written in this closed form way, which is a function of just the parameters of the model, degree, the average degree of expected degree of each node, and then these C's are just the normalizing constants of these von Mises-Fisher distributions. So this is just fully a function of the parameters and degree. Okay, now given that, we know that these YIKs are distributed approximately as Poisson with this lambda parameter from the previous slide. And then finally, the last piece of the puzzle is that it turns out that McCormick and Zhang show that this is we can write the expression for each individual's degree as a function of the gregariousness parameters. That means once we estimate degree, we can actually back out where how gregarious each of these nodes is. So that allows us to estimate these gregariousness parameters. Okay? Then the last step is to take all of those pieces, and it turns out you can write down this posterior distribution, which then allows us to estimate all of these parameters of the network formation model. Okay. So what we end up with are trait groups, individuals, their locations, their concentration parameters, and then the degree of each individual. So we can think of identification in the following way. So suppose that we have all of the centers fixed, and we have the trait groups fixed, and also their concentration parameters fixed. We can estimate Tyler's degree by expanding or contracting the radius of the circle around him, right? To match how many people he knows who have trait red, how many people he knows who have trait blue, and how many people he knows who have trait green, right? We can also then say, suppose we know where Emily, Tyler, and Mengji are living. We know how many people of red, blue, and green each of them know. That allows us to triangulate where each of those different trait groups is located. Now, the one thing that we have to do, because this is the surface of the sphere, we do need to, and you could think about flipping axes. You could flip north and south apart. You could rotate it. We do have to fix 3 of the trait groups at the beginning. So that means that when we're asking questions about this, we need to be asking at least 5 or 6 types of ARD questions. Okay, and then finally, actually not finally, step 4 is to say, okay, well, we can fill in where everybody else lives who aren't in the latent group. Suppose we know a bunch of X's, we can ask, well, who are you similar to? And then we can give you similar positions on the latent space. And then finally, we can compute network statistics of interest. So how are we doing that? Well, once we know all of these estimated parameters of the network formation model, we can actually draw graphs according to that network formation model. We can draw 500 of them and average across any network statistic calculated on those individual realizations to come up with our expected network statistic. And you can do this at the node level or the graph level. Okay. So one important question is, when does this procedure work? Now, what I just said is what we're going to do is estimate the parameters of a network formation model, draw a ton of different graph realizations from this network formation model, and arrive at some expectation of the network statistic. Now, in the real world, there's only one graph realization, right? And we care about that specific world that we live in. And so I guess the question is, when is this a problem? We care about the actual network, the actual realization. We have no idea, no way to measure that. What we're going to get instead is this expectation across all of these different draws. Okay, so there are two cases. One is many independent graphs. Turns out if we're in that world, it doesn't matter because the realization is going to be orthogonal across those different graphs. Everything's great. So the world that we really care about is going to be one of a single large graph. And we want to learn about the actual realized network statistic. So it turns out that if we're in a world where in any realization, as the size of the network gets large, that value of the network statistic approaches its mean, then the MSE, the mean squared error, from just looking at any specific draw relative to the one that we care about, is going to be getting very small. So there are going to a couple of pedagogical examples where we can think about success and we can think about failure. So the type of thing that's going to fail is if we care a lot about the existence of any given link, right? Because what our method's going to give us is a linking probability. In reality, it's either going to be 0 or 1, and so we're never going to get the mean squared error to be arbitrarily small. So if we care about whether two banks in a financial network are linked, then this isn't going to be the type of method for that type of application. However, if we think about density, now remember, we have conditional independence, and so in some sense your degree is an average over all of the possible links that could exist. So that's going to work really well. And also things that are in the class of things like diffusion centrality. So eigenvector centrality, Katz-Bonach's centrality, those are going to work really well also. Okay, so we can actually run some simulations and plot the mean squared errors. It turns out that this is the one for a single link. These are the mean squared errors for everything else. The single link performs extremely badly, as we'd expect. The thing that performs the second worst is betweenness centrality, which makes sense to us because that's going to depend really specifically on specific paths and specific links being in existence. In terms of the graph level statistic, the thing that works the worst is the number of components, which also makes sense because the number of components is very sensitive to a handful of different links existing or not. Okay. So then I can move to broader simulation results. So I'm going to go through this really quickly. But what we're going to do is just simulate a model where we know the parameters. We want to make it look a little bit like the real-world networks, where we know exactly what those parameters are. We want to ask, are we getting back those parameters in our estimation, and how well are we matching these network statistics? And so in the paper, we have a bunch of different robustness type of exercises. What happens when we vary the degree of sparsity and density? What happens when we vary the size and the sampling share of the graphs? So I'm just going to show you one exhibit. So it turns out that if we try to, we know what the parameters are, we simulate the graphs from it, and then we try to simulate the ARD responses, and then we try to go and back out degree, eigenvector centrality, and then some graph level network statistics. Turns out we do pretty well. So in these pictures, these two are node level statistics, these four are graph level statistics. And the x-axis is the estimate from the ARD procedure. The y-axis is the truth. It turns out we match really well on degree. That's not so surprising because ARD looks a lot like degree. But we also match quite well in eigenvector centrality. And then if we want to think about the network level statistics, which I think is a bit more impressive, we're matching quite well in the maximal eigenvalue, which is a measure of diffusiveness, average proximity, network level clustering. And then eigenvector cut. This doesn't actually look so good because what we're feeding in terms of where the communities live on the space on the surface of the sphere doesn't really have much of a cut structure. Okay, so things look pretty good in simulations, but what about in real-world type networks? Now the problem with real-world type networks is there's no guarantee that real-world networks look like that network formation model that we're parametrically forcing on the world. And so what we're going to do is we're going to use the Wave 2 network data of Banerjee et al., which is similar to what's behind the paper Mohammed was talking about, where we have near complete network data. We're going to construct ARD responses for 30% of the sample using a set of miscellaneous characteristics. And we want to see how well would we have done if we had collected ARD rather than the full network data. Okay, so on the network level results, This is the maximal eigenvalue. Again, we do pretty well. Eigenvector cut, we do pretty well. Clustering, we're actually going to underestimate clustering, and this is a function of the network formation model. Any network formation model with conditional independence is going to have a hard time getting the high level of clustering in the world. Now, the latent space does help us with clustering because it does assume that if two of us are close to each other and a third is also close, then it's more likely that we have a triangle there. But what it's going to miss is triangles that are shortcuts across the network. And so that's what we see. And we see that proximity we miss on the opposite side for exactly the same reason as we're missing on clustering. But I think what's nice is that we still get the ordering quite well, and we're not missing by that much. Okay. Node level results, again, we do really well in degree, not so surprising. Eigenvector centrality, we do well. And then clustering, again, we're going to underestimate the true level of clustering. And this is going to be true of almost any tractable network formation model we could have plugged in instead of the one we did. Okay. So then the part that makes me the most excited is actually, okay, well, how well would we have done in field experiment settings where the authors had access to full network data? Now, could we have used ARD instead and arrived at the same types of conclusions? So I'm going to go through two different examples of projects that I worked on and actually show that, quite surprisingly, or maybe encouragingly, we do quite well with just ARD rather than with, in comparison with using the full expensive network data. Okay. So this is a project that I worked on with Arun Chandrasekhar, one of my collaborators on this paper. And so what we're trying to think about is peer-driven financial institutions. So for example, have microfinance in your mind. Now there's been a whole lot of research about how social capital is really important in microfinance. And one theory paper by Besley and Coate wrote, the contributing member to the microfinance group might admonish his partner for causing him or her discomfort and material loss. So this is based on the idea that a lot of microfinance has groups. There might be joint liability, where if I default, actually there's some punishment on my partner. Now, in addition to those actual punishments, what we thought was interesting in this quote is that the person who has caused material loss might report this behavior to others in the village, right? Thus augmenting the admonishment felt. Such behavior is typical in the close-knit communities of developing countries. And so what we wanted to do is kind of unpack this a little bit. Is this reputation effect real? And can we try to get inside this black box of what is meant by social capital for a lot of these types of financial institutions? So we want to understand, is social reputation part of why savings groups and microfinance can be sustained? And we're going to do this in a quite stylized field experiment where we're going to randomly assign people who say they want to save more to an observer, somebody in the village who's going to just monitor what they do. And then we want to ask, does the network position of this randomly assigned monitor affect their savings? So we write down a little signaling model, and we come up with the following predictions. If the person looking at me, monitoring my saving, is more central, then I'm going to have a bigger incentive to save more because that person, if he tells other people, a lot more people are going to hear. Right? The central people speak with a bigger megaphone. And then the model also says that if that monitor is closer in the social network to me, that also might be motivating for me because the people he tells about my performance are more likely to be interacting with me on a daily basis. So any embarrassment or any punishment I get from those people who've heard, that's going to be amplified when the monitor is closer to me and we share more friends in common. And then on top of that, we have a model-based statistic that actually marries those two together. Okay. So what we're going to do is we're going to regress the model-based statistic on the right-hand side. We're going to put that as our because remember, we're randomly assigning individuals. And we're going to put log total and savings on the left-hand side. So the first column is what we get with full network data. So if that model-based regressor goes up by a standard deviation, log savings goes up by 0.25, which is a very large effect. And if we use ARD instead and estimate the model-based statistic using just the ARD rather than the full network data, we get a value of 0.18. And these two are not distinguishable statistically. So we're able to show, yes, if individuals are closer together in the social network and the monitor is more central, in fact, savings will increase as a result. The other thing we can do is we can ask, well, is this idea that the size of the megaphone is bigger for more central people, It turns out that yes. So we asked a bunch of people, what are your beliefs about how responsible the saver is? This was over a year later. And it turned out if you had a more central monitor, people had updated their beliefs more strongly. And that's true in the real data, and that's also true in the estimates from just using ARD alone. Okay. And then finally, our second application is one of network change. So what we did is we went back to slums in Hyderabad. This was the picture I showed you before, where microfinance had been introduced randomly to some and not to others. We want to ask, does introducing a formal financial product into some areas and not others change the network? Now, why might it change the network? Well, you might see crowding out, right? If we were relying on each other for informal financial relationships before, and now something formal comes, maybe I don't need those links anymore. And if it's costly to maintain those links, I might see some of those links fall away. Okay, so this is a situation where it's really impossible. The slums are so dense, there's so many people to collect network data in a cost-effective way. We don't even have a census here. We just have a basic household count, and we have ARD responses for about 20-25% of the households. So then we're going to ask, what happens to the network in response to introduction of this formal financial product, and can we replicate the findings of the original paper? So the things that we were able to collect in the original paper were degree and support. We could ask, how many friends do you have, right? That's easy. And then of those friends, how many times is there a third person who's friends of both of you? And the idea there would be that supported links are good for maintaining cooperation. And so maybe if we don't need to cooperate as much, the support rates are going to decline. And so we find that that's true in the original paper. But we can't really do anything else. We only have those two moments of the network. Okay, so what we're going to do with ARD is we're going to show that we can match the treatment effect on support. And then if you believe that our ARD model is well specified, and we think that showing that we can match on support is good evidence, then we can actually go after other kinds of graph level network statistics that were just impossible for us to look at. And this was one of the pictures I showed you at the beginning. So we can look at the change in support in the data. We can look at the change in support if we just use the ARD estimates. Turns out that, again, the coefficients are indistinguishable statistically. We find a statistically significant decrease in the likelihood that your links are supported. And then we're going to go do some estimate that is impossible to do with the direct data that we were able to collect. And we can show that the proximity at the graph level goes away. So individuals become farther apart when formal finance comes to town. This might have externalities on information diffusion, et cetera. So that's why this might be an important type of finding to look at. Okay. So I think that our view is that ARD, using these types of questions, how many people do you know who have a tractor, might be a useful way to extract information about the features of the graph, and actually are sufficient statistics in terms of identifying a network formation model. And we think it's really comforting to see that in both of our empirical examples, ARD alone could have been used to arrive at the exact same conclusions that we needed this more elaborate data collection to arrive at. ARD alone could be used to detect decreases in triadic closure in response to access to microfinance, and then allowing us, to go that extra step of measuring something at the graph level that really would have been infeasible to do. What I didn't show you was the cost savings. I mentioned this before. It's about 80% cost saving. And so hopefully we view this as just a first step in expanding the set of feasible empirical network research projects. And all of our codes, we've just gone through and revised everything, and so we've put everything up on the web. All of the estimation codes are up on GitHub, and then we have an implementation handbook along with some sample survey instruments and some pseudocodes on our web pages. And so we hope that this can be useful for thinking about other types of network applications. So thank you.
Thanks, Emily. That was super cool. Is it possible to combine this with a few seeds more and say how well can you do without collecting network data or trying to target people at all? So if you applied your method to estimate the network from the survey and then targeted people at random, just empirically, would you be close?
Sorry, can you say what you'd want us to do one more time?
Well, I want to do basically as little work as possible, which is I don't want to go and survey people, and I don't want to, right? So what I'm suggesting as a third application is kind of a diffusion application that Mohammed was talking about.
Yeah.
So would it work? Because obviously it's not clear that Mohammed's results would apply to your setting because you're not quite recovering the network precisely as you showed. Some of the features of the network are not sort of tight. But if you applied it, would you get something close? I mean,
yeah, I think that if we wanted to use our model to replicate a diffusion process, we'd actually do okay. So for one thing that, so anytime that there are multiple paths that kind of lead to the same place, things look much, much better than if we just have that one link. So one of the things in that picture, which gives me hope that we would be able to actually run experiments like what Mohammed was doing and get answers that are reasonable, is that if we say, suppose we inform somebody and we want to know how far that person is away from the seed, because that might be the regress we want to put, the mean squared error of that kind of thing is much, much lower. And I think it's really, because there are many different ways to get to the same place, there's redundancies in those paths, then the mean squared error looks a lot better. But that one link is really the killer. So I think you could actually do it, yeah.
Cool. Thank you very much for the talk. That was awesome. Can you explain why you model the latent space as a sphere instead of just say two-dimensional Euclidean space or some higher dimensional?
Yeah, so we haven't done this. So in the paper, we look at different dimensional hyperspheres, and it turns out that going one dimension up for our real-world data actually looks a little bit better. We have some ideas about how you actually might be able to estimate the right dimensionality for that space. So if you're just on a two-dimensional surface, you're much, much more limited in how the overlaps can work between different types of groups. So it's helpful to be able to put it in a third dimension. So we think that there is kind of perhaps a way to empirically judge what the right P is. Yeah.
Oh, could you say something more about how you pick the questions that you ask? Like
Yeah.
you want them to be like rare or not rare, correlated with each other or not correlated?
Yeah, that's a really good question. It's hard. So I think that there's a whole lot more to say about question design that we haven't figured out yet, but there are a couple of things that we have come to. So one, you don't want something that's completely random, because you want there to be some mass and some concentration. So twins is actually not a great example, except for the polygamous households, because you can think of it as, abstracting away from fertility treatments. It's random chance. So winning the lottery, if everybody buys a ticket, is a terrible example. You don't want things that are completely collinear with each other, because that doesn't give you any extra information. You also want to think about sort of the organic way individuals interact. So for example, we think wealth is really important. But if individuals only interact within religious group, for example, then wealth might not be so great, because wealth would be cross-religion. So you might want to think about wealth within Hindu, wealth within Muslim. And yeah, so I guess that's kind of where some pointers for this. So it shouldn't be super, super rare, but you also don't want it to be extremely, extremely common. Yeah.
Again, abusing my ability as the person sharing the session to ask a question. Could you, to solve some of these like higher order or clustering type statistics, would it be helpful to have information like, even if it's geographic, sort of some amount of segmentation that you're not just on a uniform sphere, but rather you have some information about who might be interacting more frequently or something like that?
Yeah, so I think that the limitation is really the network information model that we're plugging in, and that works better than a lot of other options, but it's still not getting all the way. So I think one approach would be to say, so Arun and Matt Jackson have a different network information model that actually allows for, so there's sort of pairs that link, but also triples fall from the sky. If you could think about plugging that in and then trying to back out an estimation procedure. Now it turns out that this one is tractable, but there's nothing to say that it's impossible. It's just we haven't tried. So I think that one intriguing future direction for research is to try to, as richer and richer network information models come up, trying to see if ARD can help with that. And my sense is that the ARD approach absolutely could work. It's not the questions and the information there. It's just our ability to kind of get all of it to work.
All right, so one point of logistics before we all sort of disperse to lunch. We're going to take a quick photo, I think, on Litauer steps. So hang around, cluster by that door, and we will walk out and do that. But first, let's thank Emily again for a completely awesome talk.